Hi everyone. In the previous lecture, we discussed about inductors. We then discussed about the process of building a current in an inductor. We said that if I had an inductor and a step current of I0 is applied across it, then it develops an impulse of voltage and builds that current I0 instantaneously. But we said otherwise, the current cannot change instantaneously across an inductor. We also said the energy stored in the inductor is half L I0 square, and we said that the remaining half of the energy actually gets lost in the resistor, source resistance Rs. The total energy supplied by the voltage source or the current source in this case is L I0 square, out of which half of it gets dissipated across the inductor, across the resistor, and the remaining half gets stored in the inductor. And we said this is true even if you assume Rs as infinity. There will be an impulse of voltage across an open circuit, so therefore you will have a finite power, you will actually have a finite energy dissipated across the resistor. The power will also be an impulse, so there will be a finite energy dissipated across the resistor. So in this lecture we will continue upon that and solve some other problems of inductors. Okay, so if in the circuit shown here there are two switches S1 and S2. The switch S1 is actually open, it's actually closed for a long time, and at t equal to 0 it is open. Here the level 1 and 0 indicates it is open, and this switch is open for a long time, and at t equal to 0 it's closed. Okay, so before t less than 0, that is for t less than 0 or before t equal to 0, the circuit reduces to something like this, and this inductor carries a current of I0 in this direction, and the stored energy in this inductor is half L1 I0 square. Okay, and the inductor builds a constant flux, so there is a constant flux that is given by L1 into I0. The flux of this inductor, once the constant current flows in it, is given by L1 into I0. Now for t greater than 0, the inductor L is now connected in parallel with another inductor L1 connected of value L2. It's connected in parallel with another inductor of value L2. Now in this circuit we are supposed to find what will be the steady state currents and what will happen to the initial and final energies. Now the instant, let's say that this current inductor L1, the current cannot change instantaneously. So if I assume that there is an I0 current present here, the L2 current, the current in L2 has to change instantaneously from 0 to I0. So therefore this will develop an impulse of voltage across it. Now since both of them are in parallel, L1 will also see an impulse of voltage. Therefore the current in L1 will also undergo a sudden change. Okay, since both are in series, the currents has to be the same, and both the currents are going to undergo a sudden change, and that I am going to call that current I dash as the final value of the current. So we have to find what is that value of current. To find that current, what I will do is I will redraw the circuit in this way. Now there is a current I0 flowing in this loop. Now I will assume phi1 is the flux of inductance L1 and phi2 is the flux associated with inductance L2. So then we know from KVL in this loop, if I apply KVL in this loop, I will get d phi1 by dt plus d phi2 by dt should be equal to 0. So this is nothing but d of phi1 plus phi2 by dt equals 0, or d phi t by dt is 0, which means the total flux associated with both the inductors does not change with time. The rate of change of it is 0. So which means the flux before closing the switch and flux after closing the switch should remain the same. So this is actually a statement of conservation of flux with time. In this circuit the flux is conserved. That's what this equation is telling us. So before closing the switch and after closing the switch, the flux remains the same. Now before closing the switch, the flux in the circuit is L1 I0. After closing the switch, the flux of the same current is going to flow through both the inductors and I'm going to call the flux is going to aid. It's an aiding flux arrangement. So the words aiding and opposing I'll discuss in more detail once we go to transformers. Here you can just take that if the two inductors are in series, both the same current is going to flow through them and the flux is going to add. So it's going to be L1 I dash plus L2 I dash. So your I dash is given by L1 plus L2 into I naught. So this is the new value of the current that is set in this loop. Now you should understand both the inductor currents change suddenly because there is going to be an impulse of voltage across both the inductors. Okay. So I'll draw an analogy between capacitor charge sharing. So we had two capacitors, say value C1, C2. This capacitor had an initial voltage of Vx, and when this switch was shorted, we said that let me just assume we'll analyze that the switch is shorted, and after that we'll try to find what is the final voltage. So we can actually apply KCL at this node and say that Q1 be the charge across C1 and Q2 be the charge across C2. Then we can say that dQ1 by dt plus dQ2 by dt, which is nothing but the current through the two capacitors, is 0. The KCL at this node will give you that. And dQ1 plus Q2 by dt is 0. So which is dQt by dt is 0, where Qt is the total charge here. Now what this equation tells us, the total charge doesn't change with time. In this circuit the total charge is not changing with the time, so therefore the charge is conserved. From which we obtain the new voltage across the two capacitors as C1 Vx equals C1 plus C2 into V dash. The new voltage we called it as V dash across the two capacitors. We got V dash as C1 plus C1 by C2 into Vx. And this result stems from charge conservation. Now this result in this here stems from flux conservation, or the rate of flux, change of flux being 0. Okay. Now we'll analyze a case where L1 equals L2 equals L. Okay. So I'm going to assume the two inductors are same, and I had an initial current of I0 in the circuit. In the steady state, once you connect the two inductors in parallel, they both are in series, currents are in the same across them. So this current is going to become I0 by 2. So that's what we found from the flux conservation. Now the initial energy stored in this inductor is half L I0 square. Now in this case, after this equilibrium is attained, the energy stored is half L I0 by 2 whole square plus half L I0 by 2 the whole square, which is 1 by 4 L I0 square. So the energy after closing the switch is only half of the initial energy. So therefore, where did that remaining half of the energy go? Okay, there is no other resistive element in the circuit. So our question naturally should be, where did that remaining half of energy go? So to prove that, I'll first assume that there was a parallel resistance Rs connected across this resistance, or I'll simply R connected across this inductance. Now this is having a current I0. Now suddenly when a current I0 tries to flow through the inductor, it will offer a high impedance, so it will flow through the resistance R. Okay, so I'm going to call this current through the first inductor as I1, the second inductor as I2, and the resistor as IR. So we have a relationship I1 minus I2 equals IR. Also, flux is conserved. Even for this circuit we can show that the flux is conserved. From that we can say that I1 plus I2 equals I0. This comes from flux conservation. L1 I1 plus L2 I2 should be equal to L1 into I0. Here L1 and L2 are same, so I have not shown the result derivation, and it's very simple. I1 plus I2 equals I0. This comes from flux conservation. Now how do I find IR? Now what I can do is that, what I can do in this circuit is, it's actually I0 into U of t, so it's a step change, so we can write it as I0 into U of t. So to find IR, first what I'll do is I'll assume the voltage across all the three elements as V and apply KCL at this node. So the current through the resistor is V by R. Current through the inductor is 1 by L integral V dt. And since both the currents are same, I am going to write 2 by L equals 0. If I differentiate this by 1 and rearrange the terms, I am going to get dV by dt into L by 2R plus V equals 0. So this is a first order differential equation, and we know how to solve a first order differential equation with zero input, so that you have to find the natural response. So it is simply V of 0 e power minus t by tau, where tau here is L by 2R. Now you need to find what is V of 0. Now if you look at this circuit, we discussed that the instant the inductor appears in parallel with the resistor, the entire current I0 flows through R. So your V of 0 is going to be I0 into R. Okay. So from that I can simply say I0 into R e power minus t by tau into U of t is going to be the voltage across the resistor. So the current to the resistor is simply I0 e power minus t by tau. It's going to start with I0, the entire current will flow through the resistor, and eventually it will go to 0. And the voltage across the resistor starts from I0 R and then goes down to 0. Now the power dissipated is going to be I0 square R, and the time constant is going to be tau by 2. So it's going to be I0 square R e power minus 2t by tau. Okay, we already discussed that the time constant for a power will decay twice faster compared to voltage and current across the resistor. So the energy dissipated across this resistor will be the area under this graph, power graph. So that will be simply I0 square R into tau by 2, where tau here is L by 2R. So you're going to get 1 by 4 L I0 square. So that remaining energy actually gets dissipated in this parallel resistance R. Okay. Now if you look at this energy, it is actually independent of R. Okay, the energy dissipated is actually independent of the value of R. Now here I am going to let the value of R tend to infinity. In that case, what's going to happen to the power is that the time constant is going to become 0. So this function time constant is going to become 0, and the amplitude will become infinity. Okay, when R is infinity, the amplitude of the power will also be infinity, and this function is going to approach 0, but the area is constant, which is half L I0 square. So therefore it will tend to an impulse of value half L 1 by 4 L I0 square, it's 1 by 4 L I0 square into delta of t. That's going to be your power, and the energy is always going to remain constant irrespective of the value of R. So what happened here was that there was an impulse of voltage across the resistor. There was an impulse of voltage across the resistor. So therefore, when the resistance value becomes infinity, it's an open circuit. But since there was an impulse of voltage across it, there was a finite power dissipated across it. The power becomes impulse. The power dissipated is also impulse across the resistor, the open element. And there was a finite energy dissipated, energy loss associated with that open circuit. And that value is 1/2 of it, 1/2 of the initial stored energy. Okay, so that's where the energy is actually lost. Again, since we have assumed as a resistor where we could actually prove that the energy loss in the resistor, again I can say this is lost as heat. Okay. So now we will again go back to discussing another problem, which is I am now going to introduce a resistor in series with the two inductors and see what exactly happens to this current in this circuit. So now again we are assuming that this inductor L, the first inductor, is going to have an initial current of I0 through it. Now you have suddenly closed a switch and this is a new circuit. Now what happens in this circuit is that again, let me just take a small break from here. So that if you look at this circuit here, I'll just give a comparison to a capacitor circuit. Okay, I think I'll spend a little bit more time on this. Let me just come back to this a little later. So what I'm going to show here is that I'll just redraw the waveforms. I'll just quickly show you the currents flowing through the two inductors, which was actually given by these two equations, which was actually given by I1 minus I2 and I1. We'll just try to find how does the currents change. So I'll just rewrite those equations across the two inductors. Okay, so your I1 plus I2 was equal to I0 into U of t, we just saw that, and I1 minus I2, which was the current through the resistor, which was I0 e power minus t upon tau, where tau is L by 2R for this circuit. Now from this we can actually show I1 is I0 by 2 into 1 plus e power minus t by tau into U of t, and I2 is I0 by 2 into 1 minus e power minus t by tau into U of t. So if you draw this graph of I1 and I2, both the inductors eventually reach a current of I0 by 2, but the first inductor starts from I0 and approaches here. Second inductor starts from 0 and builds its current to I0 by 2 eventually. Now what happens when your R tends to infinity is that your time constant tends to 0. So there will be a sudden change from I0, it will suddenly go to I0 by 2, the inductor current, the first one, and the second inductor will suddenly build a current from 0 to I0 by 2. So both the current transitions would take place suddenly, and in that case there will be an impulse of voltage across both the inductors. In the same way, we solved a similar problem concerning capacitors when we connected two capacitors in parallel of value C and C with an initial voltage of Vx across it. We showed that if you remember in one of the previous problems, if you start with an assumption that there was a finite series resistance, okay, then we actually showed that the voltages across both the capacitors will eventually reach Vx by 2. The first capacitor will start from Vx, second capacitor will start from 0 and reach Vx by 2. And we showed that the initial energy was half CVx square and the final energy is 1 by 4 CVx square, and the remaining 1 by 4 CVx square was actually lost in this resistor. So even the moment you assume that R is 0, there will be an impulse of current in the circuit, and that impulse of current flowing through zero resistance creates a finite power loss. Okay, a finite energy loss. There will be an impulse of power loss, and which will lead to a finite energy loss. We already discussed this problem extensively in one of the capacitor circuits lectures. Okay, I'm just showing it here in comparison. So in this circuit we found the steady state value using charge conservation, and we also show that the energy, the remaining energy was dissipated as heat across this resistor given by 1 by 4 Cx square. Okay, so even then we assume when R is 0, there will be a sudden change in the voltage across the capacitors, both the capacitor voltages. The second capacitor will go from 0 to Vx by 2, and then the first capacitor came from Vx to Vx by 2. Sudden change, and there was an impulse of current in the circuit. Okay, so now I'll come back to analyzing this circuit where we had an inductor of value L carrying an initial current of I0. A resistor R is now inserted in series between the two inductors. Now what will happen to the initial currents, final currents? Is there a sudden change in the currents and the final energies of the circuit? Now to analyze the circuit again, I'll redraw the circuit this way. So the resistor R appears across in series with both the inductors. I have an initial current of I0 here. Now you should understand all the three elements are in series. So this inductor is still forcing this inductor to have a sudden change in the current, which means there is going to be an impulse of voltage developed across this inductor. Okay, I mean the direction is important. I mean the sense that in this case it is going to be an impulse because the direction of current is in this direction. It's increasing, so this inductor will develop an impulse of voltage. Now this inductor will also see an impulse of voltage across it, because you have to remember that the current in the whole circuit is always finite. It's not going to go through impulses, the current. Therefore the voltage drop across the resistor is also going to be finite. It's not going to have any impulses across it. Okay, so if there is an impulse here, that has to be compensated by this inductor. This inductor will absorb that impulse because the current is always finite in this circuit. So the voltage drop across the resistor is also finite. So I can say that this inductor is going to develop. So here, if you look at this circuit, the current is flowing in this direction. So this will develop an impulse in this direction, plus minus. So I'm going to draw the impulse. Let me just draw it as a negative impulse here. I'm going to show it here. And this will develop a positive impulse in this direction. So the current will reduce in this inductor and this current will increase in this inductor in this direction shown above. Okay. So, and the steady state current can be found using the conservation of flux, and we can easily show that I dash will be equal to I naught by 2. Again, flux is conserved in this circuit. You can easily show that the flux is conserved. Okay. So that will be equal to I naught, I dash will be equal to I naught by 2. Now, there is a finite drop across the resistor because the resistor is now going to carry some current. So I will call it I naught by 2 into R. That's going to be the voltage drop across the resistor. Now that voltage drop is going to evenly distribute between the two inductors. You are going to have I naught R by 4, I naught R by 4 across both the inductors. But both the inductors, even though they have this is a finite voltage change. So therefore, because there is a finite voltage change, this potential drop will not lead to any sudden changes in the currents. The sudden changes in the current comes from the impulse of voltage that is developed because you are forcing a step change in the current through these inductors. Okay, so there will be a drop across the resistor, but that there is the only difference between the previous problem and the current problem is that there is an extra voltage drop across the resistor. What I am trying to say is that that voltage in the resistor is not going to contribute to any sudden changes in the inductor current because it's a finite voltage drop. You have to still use flux conservation to find the sudden change in the currents. The only difference between the previous circuit and this circuit is that there is a constant current always flowing across the resistor. So therefore, there is a constant power getting dissipated across the resistor for all time. Okay, as long as there is current in the inductor, there will be a power dissipation across the resistor. Okay, so which means the resistor will keep on dissipating the power until I naught itself becomes 0. So this resistor is going to dissipate all the power that is initially stored as energy in both the inductors. The initial stored inductor energy will be I naught by 2 is the current flowing in them. So it's going to be 1 by 4 L I naught square. That's going to be the energy stored in both the inductors. That's eventually going to go to 0. So that's the only difference here. But the initial value was found by I naught by 2. Okay. Again, here we can actually show that the initial energy, which is 1 by 4 L I naught square, was reduced from the initial energy of half L I naught square, which was the energy contained only in this inductor before the switch was closed. Again, the 1/2 reduction in that can be attributed by by associating it to a parallel resistance here. You can assume some parallel resistance here and show that that gets dissipated across it. Okay. So I mean, now to analyze the circuit, it's pretty trivial. Again, you can show that it's a first order circuit. The two inductors will appear like a series inductor of value 2L. If two inductors are carrying the same current, then they are said to be in series, and the inductors will add up. You will have a resistance R. Okay, so it's a first order circuit. So the current will start from a peak value, which is actually initially it was I naught. Suddenly it will change to I naught by 2. Okay, then it will start decaying down from I naught by 2 to 0 in the circuit. Now why is that decaying happening? It's happening because of the series resistance, which is slowly dissipating away the energy in the circuit. Okay, you can actually solve it mathematically as well. You will get the same solution, but intuitively to see that the decaying is happening because of the loss in energy in the circuit. Now if you see intuitively, the time constant in this circuit is given by 2L by R. You can also see that if I increase the value of the resistance, then there will be more power dissipated across the resistor. So the current will be quickly brought down from I0 by 2 to 0 faster, right? Because more and more power is getting dissipated over a resistor. So the initial stored energy, which is half 1 by 4 Li naught square, will be very quickly dissipated by the resistor itself. So that is why the time constant, that's another intuitive way of seeing that the time constant actually is inversely proportional to R in LR circuits. There's a small difference in capacitor circuits, it's actually proportional to R. So the smaller the resistance, smaller the time constant. In inductor LR circuits, larger the resistance, smaller the time constant. So in the next lecture we'll discuss in more detail about how to find the time constants and poles for LR circuits. So at that time I'll explain it better in more depth. So for this lecture I just want to take this problem, and similarly we have also solved a similar analogous problem in capacitor circuits, wherein I introduced a capacitor in parallel between the two capacitors. We showed that the instant you connect this capacitor is going to offer very low impedance, so the current is going to loop like this. Okay, so the charge sharing is going to happen between these two capacitors, and the voltage is suddenly going to drop down to Vx by 2. Okay, and this resistor eventually is going, because there is a finite voltage drop across this, as long as there is charge across both the capacitors, there will be a finite voltage drop across the resistor, so it will keep on dissipating power until the voltage across both the capacitors go to 0. There will always be some power dissipated, so the resistor will eventually dissipate all the energy present in both the capacitors. Okay, so with this I'll stop this lecture. In the next lecture we'll discuss about first order systems, first order RL circuits, and probably if there are any other problems I'll discuss it in the next lecture.